The last of the basic functions we're going to work with in this class are the trigonometric and inverse trigonometric functions. All the trigonometric functions are based on the unit circle. Each point on the unit circle corresponds to an angle, which we measure in radians. Since the circumference of the whole circle is 2 pi, everything trigonometric is going to repeat with period 2 pi. For each angle theta, we look at the coordinates of the corresponding point on the unit circle, and we call the x-coordinate cosine and the y-coordinate sine. If you drop the altitude to the x-axis, notice that this forms a little right triangle with legs cosine theta and sine theta and hypotenuse 1, since this is the unit circle. The Pythagorean theorem gives us the identity cosine squared plus sine squared equals 1. This is a fundamental trigonometric identity, and you can get 2 other versions from this by dividing with cosine squared or with sine squared. The unit circle has 4 quadrants. Looking at the different quadrants will help us understand what's going on in the graphs of sine and cosine. Here's the graph of y equals sine theta. When we start with theta equals 0, the y-coordinate, sine theta, is also 0. Then as we proceed through the first quadrant, we increase up to sine of 1. And as we move into the second quadrant, it starts decreasing down to 0. And we continue this way, we obtain this coloring of the graph. Remember, this is periodic, and so this coloring continues in a periodic fashion forever. Something similar will happen with cosine. As we go around the unit circle, the cosine starts at 1, decreases to 0, decreases to -1, and then starts increasing again. There are a lot of specific values of all the 6 trigonometric functions that you're expected to know. They're in a table on your Precalculus fact sheet. So far, we only talked about triangles that exist in the unit circle, but actually, the trigonometric functions are related to all right triangles. If we look at one of those right triangles from the unit circle, and any other right triangle with that same angle theta, they're going to be similar because they have 2 angles in common. So if we label the sides of this bigger triangle H for hypotenuse, O for opposite, and A for adjacent, think about what identities you get from the similar triangles. We get that sine theta is the ratio opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent, one of those other trig functions, is defined to be sine theta divided by cosine theta. And here in the similar triangle, we see it as opposite over adjacent. Think back, what are the other 3 trig functions, and how do they relate to this triangle? You can find the equations for these other trig functions on your Precalculus fact sheet. The inverse trigonometric functions are defined in section 1.5 of the textbook. Right away, we have a problem when we're trying to define them. The trig functions are periodic, which means that their values repeat, and this prevents them from passing the horizontal line test. So what can we do? The solution is to restrict the domain so that the resulting thing does pass the horizontal line test. So we're just going to look at a little piece of the sine function and invert that. We want to take a little piece which does pass the horizontal line test, so no value repeats, but we also want to see the full range of what sine can be. Sine can be any number between plus and -1, and we want to restrict the domain without reducing the range. There's lots of ways to do that. We usually choose the way that includes the first quadrant. So for sine theta, that means we're going to restrict ourselves to the interval from -π/2 to +π/2. Once we've restricted to this domain, the function passes the horizontal line test, and we can flip it over to get the graph of the inverse sine function. Sometimes this function is written as sine raised to the -1. It's a little confusing because sometimes an exponent of -1 means 1 over. But for the trig functions, it always means inverse. This is not the same thing as the cosecant function. Sometimes for clarity, people will write arc instead, arc sine or arc cosine, to avoid confusion. So you need to know both of these notations for the inverse trig functions. Again, when we invert a function, every point on the original curve becomes a point on the second curve with the coordinates switched. Think about how you would want to create the inverse function for cosine. You're going to need to restrict to a different domain, and then when you flip it over, you're going to get a different picture. Once you have an answer in mind, check it against section 1.5 of the textbook. Here, instead, we're going to talk not about arc cosine, but about arc tangent. And the first thing we need to do then is to remember what the graph of tangent looks like. Tangent theta is a ratio, sine divided by cosine. So whenever cosine equals 0, tangent is undefined, and we get a vertical asymptote. Between those vertical asymptotes, we have a repeating shape, which looks like this. So what is the domain that we want to restrict this to, so that we get something one-to-one, something that passes the horizontal line test, but we don't reduce the range at all? Here, we can restrict that same interval, minus pi over 2 to pi over 2, but now it has to be open. We don't want to include those endpoints where the function's undefined. And we flip it over, we get this nice curve. Since tangent can take on any value, the range of tangent includes every number, arctangent, or inverse tangent, is a function on the whole real line. You can plug any number into it. Also, those vertical asymptotes here become horizontal asymptotes. This is going to be important in section 2.7 when we look at horizontal asymptotes in more detail. Inverse tangent is also going to play an important role in chapters 5 and 7, so you'll see it again at the end of this class and in Math 152. By definition, if you compose sine with inverse sine, you're going to get the identity. But actually, you can get nice formulas whenever you compose a regular and an inverse trigonometric function, because they're both coming from triangles. What is the sine of inverse tangent 7? The key idea here is to call inverse tangent 7 theta. That's an angle we're interested in. But we don't actually need to find that angle. What we need to do is understand the triangle associated with it. So here's the triangle, and what we know about this triangle is that tangent theta is 7. That's the meaning of theta equals arctan 7. I know tangent theta is opposite over adjacent. I want that to equal 7, so I'll call it 7 and 1. And now the third side I get from the Pythagorean theorem. Now that we have all the side lengths filled in for this triangle, we can compute the sine of theta, which is 7 over the square root of 50. Think for a moment. What if I want the tangent of inverse sine 7? This is actually undefined because the domain of arcsine is only from -1 to 1. Say I put x in there instead of 7. We can proceed just as we did before. We start with setting up a triangle, and we get the function x divided by the square root of 1 minus x squared. And notice that this quantity is meaningless unless x is between 1 and -1. That's the end of our video review. It's still a very good idea to go through Chapter 1, and especially to do the recommended problems from Chapter 1.